Next, we're going to learn how to simplify radicals. Now, the radicals, what we've done so far, simplify into integer answers, like the square root of 16 is 4, the cube root of 8 is 2, and the cube root of negative 8 is negative 2. These are all positive and negative whole numbers, or integers, but not all radical expressions will simplify into integers. For example, root 16 is 4, right? But root 17 is, well, it's not 4. It's not 5, because 5 squared is 25, so it's somewhere between 4 and 5. I don't know at this point, okay? What's the cube root of 16? At this point, you don't know how to do that yet either. And the square root of 20, again, we don't know. So some of these radicals can be simplified, but they're not going to actually ever reduce into integers as they are written. So when simplifying, we need to use these steps. Step 1, factor the radicand into prime factors. Then we're going to look for groups equal to the index. For example, find groups of 2 for square roots, find groups of 3 for cube roots, and so on and so forth. So the groups will go out of the radical and be written once, and then any factors without a group will stay underneath the radical symbol. Now, if more than one number remains outside or inside, then you need to multiply those numbers. Now, I know that sounds a little confusing. We'll explain that a little bit more as we do some examples. So the square root of 12, it's not a perfect square. It's not on my list. We know the square root of 9 is 3, the square root of 16 is 4, so it's somewhere in between, but I don't know what it is. So what I'm going to do, step 1, says to split the radicand into its prime factors. So 12 can be broken down into 3 times 4. You could have also used 2 times 6. Okay, 1 times 12 is not helpful because you're not actually breaking it down when you're just dividing by 1. 4 can be broken down again. We call these factor trees. And 3, 2, and 2 are all prime factors, meaning they can't be broken down any more other than 1 in itself. So at this point, I've done step 1. Step 2, look for groups of numbers equal to the index. So the index here is 2, so I'm looking for groups of 2. Do you see 2 numbers that are just the same? Well, I do. I have 2 2's. The instructions tell me that the 2 will go out of the radicand, and any number that doesn't have a group is going to stay inside the radicand. So I'm going to write the 2 outside just once. Because I took them out as a group, I only write them outside the house once. Sometimes they call that little radical symbol like it kind of looks like a house to me. And then the 3 is going to stay inside. So I have a little story to go along with this, so I remember which one goes out and which one goes in. So let's say this is like a little house here. Okay, inside we have 3 people, a 3, a 2, and a 2. Now, in order to go out of the house, you have to have like a date. Okay, so the 2 2's, which are alike, get to go out of the house. So they're going to go out of the house, have a little fun, and come back to the house later. Okay, so the 2's go out of the house. Now, how many times do you write them? Just once, because they get in the same car when they go out to their date, right? Now, what happened to this lonely old 3 over here? The 3, he doesn't have a date, so this one has to stay inside the house or at home, okay? So the 2's go out of the house, the 3 stays home. I know it's a silly little story, but whatever helps to remember, that would be good for the test, right? So let's try this again. We have a square root again, so we're looking for groups of 2. 49 times 2 is equal to 98. And 49 is 7 times 7. 7, 7, and 2 are now prime, so they can't go any further. So I'm looking for groups of 2 because that's what the index is. So I see a group of 2, that's 7. So the 7 goes out of the house, and the lonely 2 has to stay home. And that's it. So this is considered to be more simple. 7 root 2 is more simple than the square root of 98. Still doesn't get you a decimal approximation, but it is considered more simple. So 150, one easy way to divide 150 is 15 times 10. 15 can go again, 3 times 5. 10 can go again, 5 times 2. 3, 5, 5, and 2 are all prime, and they can't be broken down any further. So I'm going to circle my pair. The 5 gets to go out of the radical. It's got a date, so it gets to go out of the house. Now this 2 and the 3, both of them don't have a pair, so both of those are going to stay home. Now the last sentence says that if you have more than one number that remains either outside together or inside together, you're going to multiply those. So the 2 times the 3 is going to end up to be 6. So my final answer is 5 root 6. So this next example is a cube root. So because there's a little 3 up here, the only difference is I'm going to be looking for groups of 3 to go out of the house. So I'm going to start the process the same. 40 is 4 times 10. 4 is 2 times 2. 2 times 5. Now if I would have started with, instead of 4 times 10, if I would have started 8 times 5, I'm still going to get the same I'm still going to get the same prime factorization. But the work may be different. But at the end, 2, 2, 2, and 5, there is only one way of making up that unique prime factorization. Okay, so I'm looking for groups of 3. I see now I have 3 2's. So the 2 gets to go out of the radical. The cube root stays a cube root. If you start with a cube root, you better end with a cube root if there's still anything left inside the house. So the 5 stays home, and then you're done. Again, we're looking for groups of 3 here, so 54, that's 9 times 6. 9 can be broken down again, 3 times 3. 6 is 3 times 2, and I'm looking for a group of 3. I have 3 3's, so that 3 goes on the outside, and the 2 stays home. The cube root, 3 times the cube root of 2. Okay, 240, that's a little bit bigger number. But I can do 24 and 10. And let's see, there's a couple different ways of doing 24. I'll choose 6 times 4. You could have chosen something else. And 2, 2, 3, 2. And then I'm also going to bring these down on the same level, 2 times 5. I like to have them all together so I'm not missing something. If I leave them at different levels, sometimes you miss them, so I like to bring them all so they're next to each other. I am looking for a group of 3 this time, so I have 3 2's. Now this other 2 is all by itself, the 3 and the 5 are all by itself, so the one group of 2 gets to go out of the house, and then all of the other singles has to stay home. Anytime you have more than one number inside or more than one outside, what you're going to do is you're going to multiply those values. So 2 times 3 is 6, times 5 is 30. And that's my answer. Okay, so the next problem is a 4th root. So we're just keep getting bigger here. So 4th is, one easy way to do that is 4 times 12. 4 times 3, 2 times 2. Again, I like to keep all of them on the same level. So even though the 2 and the 2 and the 3 didn't break down, I brought them down so that they're the same. I'm looking for a group of 4. I have 4 2's here. So this reduces to the 2 gets to go out of the radical. I only write it once, remember, because all 4 of them get in the same car. And then the lonely 3 stays home. Alright, the next problem is the 4th root of 240. Now I'm going to cheat just a little bit because I've already done the prime factorization of 240, so I'm just going to use that again. I know if I break it down again, I'll have a 3, looks like 4 2's, 1, 2, 3, 4, and a 5. Okay. Now, how is this problem different than the one we did earlier? Well, the one we did earlier was the cube root of 640. This is the 4th root of 240. So, I'm looking for 4 numbers that are the same. In this case, it was 2. Who stays home? That's the 3 and the 5. So I'm going to multiply those and get the 2 times the 4th root of 15. And our last example has variables. Okay, but it doesn't have an index, so that means my invisible index is 2. When I break this down, x cubed means x times x times x. Y squared means y times y. I'm looking for groups of 2, so I've got a group of 2 for the x. I've got a group of 2 of y's. And the leftover, the one single, stays home. So xy root x. So basically it works the same whether you have numbers or letters.